Hi, everybody online and everybody watching the recording. It is my great pleasure to welcome you all to the string theory summer class, international summer class hosted by Damgan University and taught by myself and Adrian Zaharia from University of Bucharest. So it's a pleasure to be here with all of you and to see that there is interest in Professor Zwiebach's theories and view of string theory. We are very happy to see that. I can tell you that I'm in contact with Professor Zwiebach, and he wished us the best of luck with the course. So I will keep him informed with your progress. And so, in a sense, he's near to us, and that's good. Also, Professor Benampur Hassan from Damgan is going to be near us and help us. He's going to help us with admin things, and not only he is the director of this program of continuing education at Damgan. And so he is going to assist us uploading the recordings on the site there, because what I can tell you is that the recordings will be available only for a week or two, and then they will be deleted because I don't have enough room space on my in my account to keep them forever and ever. So I encourage you, if you need to, and I will say that in the next email to the class, I encourage you to actually download the recordings as soon as possible so that you don't end up not having the recordings if you need them. That's on the admin part. I think it's pretty clear what we are going to do. There is going to be a class of 2 hours with a break. We'll take a break after 15 minutes. So the class 1 hour is actually 15 minutes and 10 minutes break. And then after the 2 hour class, Adrian Zaharia from UB, from University of Bucharest, will actually teach the seminar, the discussion section, where you are encouraged to share your views, to ask questions. Of course, you can ask questions during class as well. And also, you can ask me questions via email. I'm always available to give you answers. So don't be shy if you have things that are not clear, or simply want some clarification or some references, further references for one topic or another. You can contact me with no issues. So yeah, that's the admin part at the beginning of the course, so that this communication is going to be smooth between us, between Adrian, myself, and you. And we hope you're going to have an enjoyable experience, and that you will love actually learning string theory, because it's an exciting subject, absolutely. So I'm glad you made this choice to come here and join the class, officially, unofficially, it doesn't matter. Everybody's welcome. The most important part is that you learn. Of course, there are some admin things, also continued discussion about admin things. I'm not sure I was really clear in my last email, but the bottom line is like that. If you want a certification, you ought to, as soon as you can, it's not really urgent, but as soon as you can, you register on the site with Damgan. And in order to get this certificate, you need to pass the final exam. So there is no other requirement. We don't really penalize you if you cannot be present live for classes. I mean, you could actually watch the recordings. That's totally okay. And also, if you can come, we are glad you're here, of course, if you can make it. But you don't have to do the homework exercises either, but we encourage you that you do. There won't be that many homework assignments. It's going to be pretty light homework, and Adrian will solve those homework assignments during the discussion section. So you'll receive the exercises today. Of course, it's going to be a discussion section, but we don't have anything assigned. He's just going to work out some exercises for you to warm you up for the class. But basically, what is going to happen is that you are going to receive the homework, and then next you have a week to solve it. And next week, Adrian is going to actually do the exercises for you during the discussion section. We don't grade homework, but we assume you are at least trying to do the homework, which is going to help you out with a final exam. A few things about the final exam. For those who are interested in taking the final exam, it's not going to be something really hard. So it's going to be an open book exam. So you're allowed to use the internet, but not artificial intelligence. I mean, you cannot, give the problem to Claude or to any other AI agent to solve to give you the solution to the problem. And we will notice if you did that. So that's the requirement. You can consult the books, Wiebach book. You can consult the notes, the slides, anything you want, but not artificial intelligence, to get the answers. So the exam is pass-fail. So that's why very likely everybody will pass, because you have to solve the exam at the level of 50% to pass the course. So don't be shy. If you want to take the exam, register with Damgan, and you just try out the exam. There is no really penalty if you don't pass. It's not going to show up on your transcripts or anything, but it's an advantage if you have the official certification, I think, because then you can show you actually took and you took an exam and you passed, and you're somewhat proficient in at least bosonic string theory, which is the main subject of the class. More on admin. What can I tell you? So there will be 14 classes. The question is if, in the syllabus, I indicated that we might actually have the last class reserved for chapter 10, which is the first chapter in Polchinski's book on superstring theory. We have some information from Professor Wiebach on superstring theory. It's very little. It's about 45 minutes of slides on that topic in the Wiebach book. And it might be that we leave it at that. Have not entirely decided yet if we stay just with the Wiebach information on superstrings. Because the reason for that is the T-duality. So it's going to be really hard in one lesson to cover T-duality for open strings and for closed strings as well. So my opinion is that if we actually do T-duality for both open string and closed strings, there is benefit. Of course, there is benefit even if you do superstrings, but perhaps there will be in the future a dedicated class to superstrings. And so then you will learn in detail superstrings then, and we kind of leave it at the level of bosonic string theory, which is Wiebach book. And a little bit of an introduction to superstrings done by Professor Wiebach as well. So these are the observations, and I'm not entirely decided what to do about that. It's towards the end of the class, and we'll see about these details then. Just to have an idea of what to expect, we will follow closely the syllabus that I sent out. And so you can expect that we follow that. As I said, there will be 2 lessons for deriving the standard model from string theory, we will use a paper from 1985 by Candelas, Strominger, Witten, and I'm not sure, and Horowitz, yeah, and Horowitz. So that's the paper from 1985, which we will use in detail for showing you how standard model is derived from string theory. So we'll use that, and more than that, another paper, and so that's why we need 2 classes for that, and the Zwiebach book. So basically, other than that, which was not specifically said that we're going to use that paper, those 2 papers, actually. Yeah, it's okay, Anna, you can leave. So yeah, where was I? Yeah, still with the admin thing. Sorry, I want you to be clear on these things from the very beginning, so that you know what to expect from the class. That's why I'm taking, so much time to do this today, because then we'll embark on the course, and there won't be so much time for admin things. So basically, that's the idea with the class. It's mapped out in the syllabus. There will be exercises, homework, light homework, and 50% of the final exam will get you the certificate. So I hope that's clear. If there are any questions. No questions. Okay, so everybody very clear on admin. If there are still questions, you can shoot me an email, which is okay. If you have difficulties signing up on Damgan's site, you also shoot me an email, so I can try to help you out. You can also email them separately. There is an email address on the poster. So you can either email me or them if you have difficulties signing up. Again, you actually have to sign up with Damgan in order to be certificated. You can also, of course, take the exam and not get the certificate. That's also an option, but you're strongly encouraged, if you take the exam, to actually register and get the certification. Okay, wonderful. That was it with the admin. Now we can start. Let me see, where are the slides? Okay, so this is the slides are part of a course that I taught a few times at University of Bucharest. And initially the course was designed, that's why it's lesson 7. You may wonder why it's lesson 7 when we are actually on lesson 1. It's because this course was initially designed as a combination of general relativity and string theory. So the first 6 lessons were on general relativity, and the other 7 on string theory. Meantime, we have expanded, and we go over Zwiebach's book until chapter 18, and then jumping to 22. So basically, that's why. And I think we can start now. Okay, so we will leave the supersymmetry part towards the end of the class, and we will start with intuitive facts about intuitive presentation of string theory. And this information actually was taken mostly from Brian Greene's book. Let me open the whiteboard. I have a whiteboard here open for you. Let me open it. Okay. Adrian se vede whiteboardu?
Da, tot e ok.
Adrian, can you see the whiteboard?
Yes, everything is alright.
Everything is okay. Okay. So yeah, so I recommend this book as an additional reading. It's Brian Greene from Columbia University, and he's joined in the math and the physics department. So Brian Greene, Fabric of Space-Time. It's an older book, but it's pretty good. And it presents you with intuitive facts about theoretical physics, particularly string theory. So Fabric of Space-Time. I think you can still buy it on Amazon. Okay, I'll write it here so that you have it. It's a little cumbersome to write on whiteboard, but get this book and read it in your spare time. You won't be sorry if you do that. So Brian Greene is a distinguished professor from University of Columbia University in New York City. And what I can tell you is that one of the distinguished professors at University of Bucharest and the Institute in Magurele is a Professor Călin Lazaroiu. And Professor Călin Lazaroiu has a double math and theoretical physics PhD from Brian Greene from Columbia under the supervision of Brian Greene. And so he's one of the pillars of string theory at the institute, the Theoretical Physics Institute in Magurele, joined with University of Bucharest. So so I wanted to mention that. Okay, so let's now embark on this journey together. There was a need of reconciliation between quantum mechanics and general relativity. Some of you may be familiar with quantum mechanics and with general relativity. It would be good if you had some notions, at least if you read a few things on Wikipedia. If you don't have time to take a quantum mechanics book and study a little bit, and also general relativity, because we will use some notions from quantum mechanics and general relativity. And as a general relativity, just a second, let me go back to the whiteboard. I think it's called, it's Carroll's book. It's a beginner's book in general relativity. If you want to just browse through it, I think it's called General Relativity, maybe called differently, but in any case, it's just one general relativity book written by Carroll. So Carroll, General Relativity, that would be fantastic if you go through the first few chapters, 3 or 4. That will be helpful to understand, for instance, what a metric is. We'll introduce the notion of metric today, but of course, that's just very little. So in order to understand a better the notions in string theory, I think a bit of general relativity can help you out. So the first book I recommended is Brian Greene. The second one is Carroll, General Relativity, or something like that. Not sure the title. So anyway, let's go back to our slides. So quantum mechanics rules at small lengths, general relativity governs on large scales. This thing with a reconciliation between quantum mechanics and general relativity goes back way before our times, when Professor Bohr and Professor Einstein had a discussion on these things. Basically, Professor Einstein said that very famous quote that God does not play dice. And basically, he always tried to make Professor Bohr uncomfortable, who was one of the fathers of quantum mechanics in those days, in the beginning of the 20th century, and always came up with situations in which he believed quantum mechanics would break down. The system with working with probabilities and things, and with operators and wave functions and so forth that are typical to the Copenhagen quantum mechanics school, which was designed by Professor Bohr and his collaborators. So Professor Einstein did not believe quantum mechanics that much. And he always teased Professor Bohr on that and came up with little experiments or little thought experiments or ideas that would make quantum mechanics break down. Each time Professor Bohr got scared by the counter examples Professor Einstein came up with, but nevertheless, in about a few hours, he was able to solve those conundrums and get back to Professor Einstein and tell him, look, this is like this. It actually holds quantum mechanics, I'm sorry to tell you. Now, of course, it may sound surprising that Professor Einstein was at odds. So general relativity at that point in time was at odds with quantum mechanics. It may sound odd to see that, but there are paradoxes everywhere in quantum mechanics, in theoretical physics, and so forth. And the paradox here is the fact that actually Professor Einstein had big contributions to quantum mechanics. One of the most famous contributions is the photoelectric effect paper in 1905. He explained the photoelectric effect, which is a quantum mechanical effect that involves electrons and photons. So that was one big contribution to quantum mechanics coming from Professor Einstein. And it's not the only one. The other one, which is remarkable, is the Einstein-Podolsky-Rosen paper. I think it's in 1930s or something. The Einstein-Podolsky-Rosen and the Einstein-Rosen bridges, where basically he introduces the notion of non-locality in space-time and quantum mechanics, and the link between quantum mechanics and if you want, space-time, general relativity in a sense. So he already devised this link that made Professor Susskind nowadays say that GR equals quantum mechanics. So at this point in time, there is no more problems. There are no more problems between quantum mechanics and general relativity. So all smooth and good. But going back to the Einstein-Rosen bridges, which are again a big contribution from Professor Einstein in quantum mechanics and the link between quantum mechanics and general relativity, it's basically introducing the notion of wormholes. Wormholes are actually solutions of general relativity, but they can also be viewed in quantum mechanics as correlations between two quantum particles. So if you have a strong correlation between two particles, then a wormhole forms. So there you go. Quantum mechanics is intertwined with general relativity. And Professor Einstein and Rosen, actually, these two professors made that clear back in the 30s. So, as I said, paradoxically, Professor Einstein nagged at Professor Bohr about how quantum mechanics doesn't work, alongside the fact that he himself had contributions to quantum mechanics and the intertwining of quantum mechanics and general relativity. So these are the fun aspects of things in physics. But that's how things developed in the course of time. And that's history, and it's physics history, and it's fun to recall these things. Of course, nowadays, the advent of wormholes is really big. I can tell you just one thing about wormholes, because they actually proved that wormholes exist. So it's not just an artifact in theory with black holes and things, because wormholes are linked to black holes. It's just something that um, actually was proven to exist. And that was done in 2022 by Professor Jafaris from Harvard University and collaborators. So basically what they did, they were not after proving that wormholes exist. That was not their fundamental quest with the paper they wrote and the experiment they carried out. They had different goals, but in the process of achieving their goals, they also proved that wormholes exist. So basically, there were two chips, quantum chips, from IBM. So they worked with two quantum chips on two sort of quantum computers, if you want, from IBM. And they made a strong correlation between particles on one chip and particles on the other chip. And that, of course, as we have just mentioned, if you have correlation between two quantum particles, then a wormhole forms. And so there was a wormhole produced, which lives in 5 dimensions. So ergo, not only they have proven that a wormhole exists, but also they've proven that space-time is more than 4-dimensional. It's 5-dimensional. If you have a wormhole, you go into 5 dimensions already. So that was big, in my opinion, as a sidetrack from what they were actually trying to achieve with a SIG model, the double-scaled SIG model, which is beyond the scope of this class, which is quantum gravity. I have a quantum gravity class. Whoever is interested in joining the quantum gravity class, I'll in the next email I'll send you some information about that. It's not from Damgan. The quantum gravity class is independently run by myself and University of Bucharest. So that's another class. It runs on Fridays from 2:30 p.m. Bucharest time for an hour and a half until 4 p.m. Bucharest time on Fridays. So whoever wants to join the quantum gravity, you're welcome to do that. It's not with grades or registration or anything. I just put you, if you're interested, you shoot me an email. And I put you on that list of the quantum gravity class, which will run for a few months. It's towards the end of the class, I agree. But the modules are independent. So basically, if you join a module, we just started another module. You don't need that much background from previous classes, actually, because they are self-contained. And we go over papers anyway, so I'm using your time here to advertise that class. Sorry about that. But I'll send you some information when I send the recording of this class. So anyway, let's go ahead. Quantum mechanics rules at small lengths. General relativity governs on large scales. Quantum mechanical vacuum fluctuations are proven by the existence of Casimir force, effect found by the experiment. So a little bit about the Casimir force. So basically, at the microscopic level, you imagine there are two plates. Basically, they're very close to each other, on a nanoscale or things like that. I mean, small scale, micro, nano, small. What happens is that they noticed that because of the vacuum fluctuations in between the plates and outside the plates, there's a difference between inside and outside, then the two plates are pulled together by a Casimir force. So that's with the Casimir force. Okay. Here it's a statement. We've also seen many confirmations of general relativity in the first part of this course. Yeah, there is no first part here, such as the curvature of light in strong gravitational fields. Okay. You'll excuse me, I don't have special slides for you. I'm fairly busy, so I apologize. I didn't fix the errors, the typos. They're not per se big errors, but there are typos of all sorts in these slides, and I haven't fixed them. Basically for two reasons. One is lack of time. Secondly, is the fact that I am Professor Gary Gibbons' student, and Gary had this fantastic way of, moving fast through things and publishing so many papers and leading so many students. And he lacked time too. And so he typed very fast the notes of his course, which were marred by typos, to the point that when I was in Cambridge, one of his differential geometry courses, I was in jeopardy of not understanding certain things because of the typos. I tried to wrap my head around his notes. But then after a while, I understood, and I thought, wow, if there were not for those mistakes, I wouldn't have understood things so well. So then I thought, now it's my turn to teach a class. I learned from that. It's actually a good learning experience if you need to make an effort to understand the formulae. And that's why I didn't fix them. One reason. I thought it's challenging for you to try to figure the things out for yourself. I think that's important. Okay, we have about 10 minutes left, and then we'll take a break. And I'll move faster from now on through the slides so that we can finish in the second hour. But if there are any questions of any sort. Okay. All right. So it turns out that space-time fluctuates as well on very small scales, and so that the regime is governed by quantum gravity. Quantum gravity is the marriage between general relativity and quantum mechanics, and can be resolved in the realm of string theory. Of course, not only in the realm of string theory. Loop quantum gravity does a great job also. And there are other avenues. Samir Matur, for instance, has some theories with the fastballs, and I forgot the term. It's a Veckers or something. It's not that term, but he has something in lieu of string theory and loop quantum gravity, a new perspective of what happens at the microscopic level. Yeah, it's interesting. Maybe I'll send it as a bibliography, as a reference for outside reference for whoever is interested in alternatives to string theory. But of course, the most developed is string theory, obviously, as a theory of quantum gravity. Then comes loop quantum gravity, and there are others, other backgrounds and frameworks as well. So one major goal of string theory beyond the unification of quantum mechanics and general relativity, which was achieved, is to unify all four or five, I mean, if we consider dark matter as well, known forces, and to provide a systematic framework to describe all matter in a unified way. So yeah, that's one of the goals of string theory, to unify things. we'll see a little later on the slides the unification of gravity and electromagnetism in Kaluza-Klein theories in 5 dimensions. And it's a little not so accurate that string theory is a theory of everything. What nowadays string theory does is it goes on the realm of the lamppost. So we won't really study swampland and landscape theories in string theory, because that's so we won't study the swampland criteria for string theory. The other theories, which are effective field theories, if they're derived in UV from quantum gravity or not. But it turns out that string theory has this goal of understanding everything in the domain of the lamppost. And perhaps at some point there will be a course on distance conjecture, weak gravity conjecture, and so forth, and the delimitation between swampland and the landscape in string theory. I won't go over these things at this point, just to mention, or you can look up swampland and you can learn a little bit about that if you're interested. Okay. Yeah, I was talking about swampland because this program was initiated by a number of people, including Kumrum Vafa. Kumrum Vafa is string theorist, a famous string theorist. Yeah, we have to also learn who's who in string theory. We don't. The human interactions and also history of the field are very important to know who contributed. Obviously, Professor Puczynski, Professor Zwiebach, but also Professor Vafa is one of the landmark figures in string theory. And he's a professor at Harvard, and he's originally from Iran, Professor Vafa. I was enrolled at some point, as you know, from my bio that I sent to everybody. From my bio what I did. When I was in the States, I studied for a while at Brandeis University, which is a Jewish university in the Boston area. My advisor at Brandeis told me, okay, now you want to study string theory, right? Right. He said, okay, now Professor Vafa at Harvard is teaching a string theory course. Why don't you go and audit that course? Because it was possible from Brandeis at Harvard and MIT to go and listen to courses there. And I went to Professor Vafa's course, and I can say that Professor Vafa is the first one who taught me string theory, and I'm very proud about that. That's the link I have. Well, I have some links at MIT and also at Harvard, but this was my first string theory course taught by Professor Vafa, and was nice and neat. And he talked about bosonic string theory and also superstring theory. And it was a wonderful course. And I thought he did a marvelous job with us there, teaching us string theory. I cannot raise to that level. This course is not going to be like that class at Harvard. But I'm trying to do a decent job with it so that you feel comfortable and you learn something in string theory, and you end up with some information which is valuable, and also a little bit of history of string theory and some anecdotes from the realm of string theory with some professors that I interacted with, like Professor Daniel Waldron from Imperial College. So he was my advisor there, and he worked. He's now more into the math realm, but of course, string theory and math are connected. So he's one of another pillar in string theory from Imperial College, Professor Daniel Waldron, and Professor Călin Lazaroiu, of course, from Romania, is pillar too. And there are other many people who work in string theory or quantum gravity, with which I had the honor to interact with. So, what is string theory and how did it come about? Well, it came about back in 1967 when Veneziano tried to give an explanation of the nuclear strong force. So, ironically, string theory started in nuclear physics, actually, because he devised a paper and experiments with experimental data to explain that experimental data coming from the strong force in nuclei. The beginning was really string theory tried to explain the strong nuclear force. Then Susskind, of course, Professor Eleni Susskind, and Professor Nielsen explained his findings about the nuclear force with the help of a string. So there you go, a string appeared, so a one-dimensional object. So string theory was born. But there was a lot of skepticism about those things in the beginning. Now, in the early 70s, Schwarz and Schreck moved the realm of applicability of string theory from the strong force into the arena of quantum gravity, explaining that the graviton, a spin-2 particle, is the carrier of the gravitational field, and that strings should be really tiny in order to explain the feebleness of the gravitational force. So Schwarz and Schreck, not Shrek. The movie Shrek, yeah, it's Shrek. Schwarz and Schreck moved the realm to quantum gravity. So those are the fathers who actually brought us here today, together with Veneziano, Professor Susskind, who's everywhere, from black holes, string theory, you name it, complexity, quantum computing, whatever is new and cool, Professor Susskind is in there. Yeah, and he was invited together with Professor Witten to Damgan University to give talks at a conference last year, and they agreed to do that. And so they're friends of Damgan, particularly Benam Purhasan, they're great friends of Damgan University, Professor Susskind and Professor Witten. So that you know these things, as I said, I'll tell you these little secrets of the theoretical physics community so that you learn who's who in string theory and what they do. Okay. For string theory to be a viable theory, it needs to be an anomaly-free theory. Anomalies are infinities in the theory that sometimes occur when we switch from a classical picture into the quantum realm. So you have a symmetry in the classical realm. When you switch to quantum theory, that symmetry may be broken. It may not hold anymore in the quantum realm. So if that happens, there are anomalies. String theory is a theory of quantum gravity, so quantum nature. There are no anomalies in string theory because, for instance, in 1984, Schwarz and Michael Green proved that if we move the theory in 10 space-time dimensions, the superstring theory, a supersymmetrical theory of strings that contain both bosons and fermions, is anomaly-free. We will see in class also for the bosonic strings we will see how Professor Zwiebach makes the case that there are no anomalies if the bosonic string lives in 26 dimensions. We will see that later in class. So that's why the bosonic string lives in 26 dimensions and the superstrings live in 10. And M theory is in 11, and there is also a possibility to have F theory in 12 dimensions. So all these things are, all these theories are valid string theory theories. Okay, now it's time that we take a short break, 10-minute break. I'll leave the connection open, and we'll see each other back at around 6 p.m. So in 10 minutes, back to our class. Thank you for your attention. Enjoy the break. Okay, welcome back. I hope everybody had a chance to relax a little bit. And we will continue with the slides. Okay, so 1984 was an important year for string theory, and it was considered the year of the first revolution in string theory. So this is one. There was one in the 90s as well. So these two points in time, 1984 and mid 90s, mark important scenarios for string theory. Um, we will also study a little later a spin-off paper, as I mentioned, in 1985. Candelas, Witten, Strominger, and Horowitz wrote a seminal paper on deriving, if you want, the standard model-like theory from string theory. So that was a seminal result in 1985. So shortly after the Schwartz and Michael Green breakthrough with the 10 dimensions in superstring theory. And I can tell you that at that point in time, 1984, 1985, there was another paper on introducing the heterotic string theory model. It's one of the types of the 5 types of string theories that we know of in 10 dimensions. And after that came the paper we will study in this class in 1985. So there were a number of, that's why it's called the revolution, because there were a number of contributions at that point in time, starting with Schwartz and Michael Green and following with the others. And it was really a boom at that point in time. So superstring theory came out of the closet, so to speak, came out into the world and gained acceptance, because a theory can be nice and good, but if it does not have acceptance, then it remains in a drawer, hidden there until somebody can make it viable and accepted, and then tested somehow, theoretically or experimentally. Um, so we'll talk about these things with a particle physics perspective, and string theory will have a designated class in which we will see how the standard model comes out of string theory. And that thing that string theory does not have predictive power and all that, it's not true. String theory has predictive power, and it can actually bring a lot of substance to the table. Not only the unification part, but also the predictive part. The fact that it can derive the standard model, which is such a successful theory in particle physics. Okay. Okay, here a little bit about the quantum fluctuations. I think we discussed that. The 10 to the minus 33, the Planck length, and the Planck time, and the Planck mass, all related with that Planck scale of 10 to the minus 33 centimeters, which is a landmark again. So here I would probably want to go a little bit over these things. So the cosmic fabric of space-time. In a sense, these things are not so accurate anymore at this point, because nowadays there exists a lot of transplanckian lengths and particles and energies. So theories have actually gone beyond the Planck length, because if you put a marker for theorists and for scientists, and you say don't go beyond that point, for sure somebody is going to go beyond that point, because it's exactly like that. If you say no, 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 don't go beyond that point, for sure somebody will go beyond that point. It's a rule of thumb in science and theoretical physics. So of course, if we set a scale like the Planck length, and we say that's the smallest, for sure somebody is going to come and go beyond that and find transplanckian energies and things, which are not very scary actually. And in the quantum gravity class, we discussed those things in detail, how it is with the transplanckian energies. But anyway, in this original view of the fact that the space-time, I mean, there is some merits to look at the Planck length and to view the space-time, because that grid actually exists in reality. And in a sense, space-time is a discrete thing. It's not continuous as we are used to at the macroscopic level. At the microscopic level, the space-time is a grid. And let me show you a picture which follows here. Now I'll come back to so this is a grid. You see the grid, and this is a Planck length of the grid. So a grid with Planck lengths. Beyond the Planck length, there are entropic entities which actually generate the space-time. But you can think of these strings that form a grid, which are of length 10 to the minus 33 centimeters. And at each point on the grid, there are Calabi-Yau manifolds. These interesting pictures of something that's 6-dimensional, and you see here a cross-section in 3 dimensions. I mean, it's a 3-dimensional picture. Of course, nobody can actually that easily represent something 6-dimensional on a piece of paper. It has to be a cross-section from 6 dimensions down to 3, max 3, because we are 3-dimensional space creatures, and that's what we see and do in 3 dimensions, plus time, that's 4 dimensions. But anyway, these Calabi-Yau manifolds are small. We will in a moment go back and discuss Calabi-Yau manifolds, but I just wanted to show you the grid, which is courtesy of Brian Greene. This is from Brian Greene's book, this image. Yeah, the book I recommend that you read. So I'll get back to Calabi-Yaus in a moment. But let me okay. So the fact you have to remember here from this slide, the fact that space-time is a grid, is discontinuous. It's discrete. So one other thing that you ought to remember from this introduction is the fact that the vibrations of the string produces various vibrations, produce particles. The particles and the matter we are used to. Of course, we know from quantum mechanics that there is duality between particles and waves, the wave-particle duality by Louis de Broglie, and we know those things from quantum mechanics. So it's no wonder the fact that if you have a wave on a string, just like the violin, only these, when you play the violin, you modify the length of the string, and you provoke a sound by actually exciting the chord of the string of the violin. And it's pretty much like that in string theory as well, only the strings are very small, technically speaking, and there are vibrations just like on a violin chord on that grid. And then what you can see is the vibrations produces wave. By the wave particle duality, that transfers into particles like electrons, like the quarks, like the photon, like the W plus minus Z0, the gluons, the graviton, and so forth. And we will study these things in detail, not the fermions in this class, just the bosons. So basically, we won't get to gluons either, but we will get to the photon and the graviton and other particles. Young-Mills that produces gluons is not covered in the basics of the bosonic string theory that we cover, in this class. So we will see how comes that the bosonic string theory lives in 26 dimensions later in the class. And of course, to describe, there will be in that class dedicated to how the standard model is derived from string theory. There will be an incursion into heterotic string theory, which is a superstring theory. So we will have some notions of superstring theory at the end of the class, as I promised. But again, not sure if we will cover the first chapter in volume 2 of Polchinski. Not sure about that, but you will get some notions of superstring theory nevertheless. So the vibrational particles, how the mass, the Planck mass is 10 to the 19 mass of the proton, and so forth. So extra spatial dimensions in Kaluza-Klein theory. As I said, 1919, Kaluza proposed the unification of gravitation with electromagnetism in 5 dimensions, generalizing Einstein's equations. So he proposed a higher dimensional version of Einstein equations, which are written for 4 dimensions, which also entail having extra equations added. So to Kaluza's surprise, these new equations turned out to be Maxwell's equations, which govern electromagnetism. So the natural dimension where first unification takes place between gravitation and electromagnetism, it's 5. Unification of strong force and all the other forces occur in 10 dimensions. In 26 as well, only we don't have fermions, we don't have electrons, we don't have quarks. It's just a theory of bosons, what we're going to study mostly in this class. As I said, we'll have some coverage of for superstrings as well, but just a little. Okay, then Kaluza in 1926 came up with another revolutionary idea, namely that the 5th dimension proposed by Kaluza is compact and tiny. And this idea spawned from the fact that in reality the extra spatial dimensions could not be observed. So, we now are able, as I said, to observe the 5th dimension, which is not necessarily very tiny. But at that point in time, they did not have the technology to jump into the bulk as we have today. The bulk, just to have this notion of what the bulk is and where that 5th dimension from Professor Jafari's experiment comes from, I will just briefly explain ADS-CFT, which is this theory, which is something very nice and fairly complicated. And I don't have the space now to get into all the details. But what interests you here is to understand the bulk, what the bulk means. And I can tell you the bulk is that space-time which has a boundary. And we live, our brain lives on the boundary of this space-time, presumably. And the boundary is always one dimension lower than the bulk. I mean, for a sphere, you have the volume of a sphere, which is three-dimensional, but the sphere itself is two-dimensional. So the ball is three-dimensional. The sphere is two-dimensional. The surface, basically. So in that respect, we live in four dimensions. That's the boundary. And the bulk is something five-dimensional or higher dimensional, at least five-dimensional. So we already are in the bulk. We have connection with the bulk, even if it's just via the experiment of Professor Jafferis. And that's a reality, that there are more spatial dimensions than just three, at least four. We already have proof for that. Okay, but of course, in 1926, they didn't have this technology with quantum computers and things. And I'm not even sure that at that point in time, Professor Einstein and Rosen wrote their Einstein-Rosen paper in non-locality in quantum mechanics. So, that's why they said, well, it's compact and tiny. And we think still that this compactification is something reasonable, because in everyday life, you actually don't have access to the bulk. And it's a good view to see space-time as that grid with Calabi-Yaws, six-dimensional Calabi-Yaws at each point in space, and together make 10 dimensions. So six really tiny Calabi-Yau six-dimensional manifolds at each point on the grid, and the grid is four-dimensional. And the Calabi-Yaws are six-dimensional, together 10-dimensional. The 10 dimensions the superstring theory lives in. Okay. So, any questions? It's okay. It means everything is crystal clear, which is good. If everything is crystal clear, remember, some people will take an exam, of course, not from necessarily these ideas, intuitive ideas about string theory. But it's always good to plan ahead. If you plan to take an exam, don't leave material not understood until the last minute, when we will probably have a session to help you out with the final exam. Namely, there will be 1 hour of answers and questions and answers before the exam. But don't leave everything on the last minute. So you think about these things when you leave the class. And if you have questions that pop up after you leave the class, you can either email me or ask questions next time in class. And don't be shy. It's just us. It's a recording. I agree with you. But, it's just who's going to watch? Just people in the class, basically. And perhaps Benham, but I don't think Benham has that much time to watch the classes. So it's just Benham and us, the members of the class. So don't be shy. Yeah, it's just the first lesson. Things are fairly straightforward, I guess, so far. Okay. Okay. So this new theory was dubbed Kaluza-Klein. So this five-dimensional theory, which is a unification of electromagnetism and gravitation, was dubbed Kaluza-Klein theory. Then you compactify the theory on one circle, the fifth dimension on a circle, and you end up with a four-dimensional grid and circles like that at each point in time, tiny circles. And what's left, what's left in four dimensions. In five dimensions, you have like matrices, 5 by 5 matrices that describe the content of the unified electromagnetism and gravity. And after compactification, the two decouple. You have gravity in form of general relativity, and you have electromagnetism in form of Maxwell's theory. So we don't show here too much detail about Kaluza-Klein, but you know, in four dimensions after compactify, what do you get? You get the metric. Not sure if you're familiar with metrics. That's why I recommended that you take a look at Carol, who discusses a little bit the notion of metric. Now I don't have that much time now too, because I have to catch in half hour. I have to finish. But if you're not clear on what the metric is, you can ask some questions privately or next time. So the five-dimensional compactified effective theory has a spectrum. I mean, what does it contain? A spectrum contains particles. The graviton classically, it's a quantum mechanical thing, of course, but classically it is described by the metric, the curved space-time metric, which is g mu nu. A mu is the vector potential corresponding to the electromagnetic Maxwell field's potential. Of course, it's the vector potential. And K is a massless scalar called Kaluza-Klein scalar, and was later dubbed the dilaton. We will see a dilaton in the closed spectrum, which naturally emerges in the closed string theory spectrum later in the course. When we'll see it's coupled with the graviton and the Kalb-Ramond field, and as the dilaton is a scalar, and it's used in cosmology a lot. You can look up dilaton, for instance, even the graviton, which is spin two particles, but for our purposes, is described by G mu nu. We'll see in class more about how we express this object called the graviton, which is basically quantum mechanical in the end. Let me backtrack here a little bit. To describe Kaluza-Klein theories, we need a periodic fourth spatial coordinate. So in five dimensions, you have z plus 2 pi l, where is a fundamental length related to the radius of compactification, which is rz. So compactification means you roll the space-time around a circle. So there is a periodicity on the circle that comes, 2 pi l comes, if you want, it's the length of the circle with a radius r on which you compactify. So you roll the space-time on that dimension. If you want, I can, but it's like a cylinder, basically, the space-time. So you have the space-time rolled like a cylinder on the circle. If you want me, I can draw a circle or a cylinder on the whiteboard, but I don't think I will do that because I think you got it. Okay. So a metric. This is an example of a metric 20 for the five-dimensional Kaluza-Klein metric. This is Minkowski metric, and this is the metric together with eta mu nu is the Minkowski space-time. And the fifth dimension is this one, compactified on the circle is the cylinder. On DZ, the special coordinate, which is the fifth dimension, which is compactified like that. It's rolled on the circle. So modern Kaluza-Klein theories are characterized by internal symmetries and supersymmetry algebra. We'll go over supersymmetry towards the end of the class. And it can be reduced to four-dimensional effective theory with an appropriate spectrum. Okay. Yeah, we're getting a little technical, so you have to be on your tiptoes to follow. Okay. The shape of hidden dimensions. So according to superstring theory, the world is 10-dimensional, given the fact that anomalies cancel in 5 dimensions if the manifold on which string theory lives is 10-dimensional. So only in 10 dimensions or in 12 dimensions or 11 dimensions or 26 dimensions, these anomalies cancel. So you have no infinities in the theory. Everything is clean and nice. It turns out that the 6 compactified and hidden dimensions could be Calabi-Yau manifolds, named after 2 mathematicians who discovered them. We'll go over properties of Calabi-Yau manifolds in that lesson associated with chapter 15 in Professor Zwiebach's book, so towards the end of the class. Okay, so the picture with the grid and the Calabi-Yau manifold, we saw that. Strings vibrate in all 9 spatial dimensions. Vibrations which are influenced by the shape of the hidden, compact, tiny Calabi-Yau manifold. So the precise size and shape of the extra dimensions has a profound impact on the string vibrational patterns and hence on the resulting particle properties, which are intimately linked, like we will see, to the topology and properties of the Calabi-Yau manifolds. So the particles which we are so used to, the electron, the quarks, the photon, I'm sorry, I need a break. I talk too much. I should let Adrian talk as well. My voice is coarse. Yeah, we should take turns. He should talk too during class. Anyway. Okay. So the precise size and shape of the extra dimension has a profound impact on the string vibrational patterns and hence on the resulting particle properties. So these particle properties of the spin, the mass, you name it, of the electron, quarks, photon, graviton, and so forth, are intimately related to the shape and topology of the Calabi-Yau manifolds. And so it's an intertwined thing between space-time and the particles, because particles depend on what kind of compactification, their properties, you do. So what kind of manifold you have at your disposal. And somehow you have to derive, as we will see, we derive the properties of the particles and the spectrum that we see in stellar model from this compactification from 10 dimensions down to 4 with 6 compactified dimensions, which are a Calabi-Yau. We'll see these things in chapter 15. Okay. So that's, we covered that. We covered this too. I think we'll skip the Higgs mechanism. It's a mechanism for this particle Higgs that gives mass to the particles, all the particles, and it's used in string theory as well. And for which a Nobel was awarded in 2013 to Englert and Higgs, of course. And the thing is, some people were left out from the Nobel, like Professor Kibble, who worked on this mechanism, on the Higgs mechanism as well. But, nobody can actually make things incredibly fair for everybody. So Professor Higgs from Professor Kibble from Imperial College didn't get a Nobel, but the Queen of England actually gave him the title of Sir. So in the meantime, he passed away. He was kind of elderly, of course, at the age of Higgs, maybe more than Higgs' age. And so he got that instead of the Nobel. Nobody can make things fair in science either. There is no fairness or very little in life. Um, I speak from experience. There's very little fairness that they couldn't award six other people who worked on the Higgs mechanism the Nobel, because that would have fractioned the Nobel down to very little money for everybody, and so they couldn't give it to six people, including Professor Kibble from Imperial College, who got other forms of recompensation for what they did, like Professor Kibble got a honorary aristocratic title of Sir. So, there is always compensation. Somehow, I said it's unfair. Yeah, it's unfair, but then life is unfair, but then there come compensations from God or from somewhere else, and which indirectly from God, basically. So, if you are in an unfair situation, don't worry, because help is on the way. So, in the end, God will recompensate everybody who got stuck into an unfair situation, like there are so many on Earth, which we know of. Not going to go into the details now, just mentioning them. Because I said life is unfair. Yes, it is, but there are compensations from God. Okay. Okay, so the 5 superstring theories, which we will take a look at only heterotic E in more detail from these 5 superstring theories. The heterotic E closed strings only the symmetry group. We'll go over these things: 8 exceptional group, 8 times exceptional group 8, chapter 15 again. We'll hear a little bit about type 2A and type 2B from Professor Zwiebach. And we won't hear that much about heterotic O governed by the internal symmetry group of SO32, or type 1, which contains both open and closed strings. All these things are covered nicely in volume 2 of Professor Polchinski, which is the topic of another class. Perhaps we will do it ourselves later. Not sure when, but it's an interesting book, Polchinski. Professor Zwiebach covers the basics, and Professor Polchinski covers the more advanced stuff. So the dualities, yeah. What can I tell you? S duality is a duality that transforms strong coupled systems in low coupled systems. T duality, small scale to large scale, and U duality, a combination of S and T. We'll study T duality in detail for bosonic strings. Okay, the second superstring revolution in the mid-90s, Edward Witten and Peter Horava discovered an 11-dimensional theory, M theory. We'll have a chance in chapter 16 to see a little bit of M theory as well. So we're going to discuss a little bit in chapter 16 a paper of mine written with Professor Joseph Bernard from Saclay, Paris, France. In that paper, we'll get to see a little bit about how M theory works, and how the compactification of M theory down to 4 works as well, in the context of black holes. So you'll see a little bit of M theory, just tiny bits of everything. But later you can go into swampland. I mean, not stay in swampland, God forbid. But you learn about swampland, and about the landscape and other things, and about superstrings in detail. If you're interested, of course. I mean, some people want to make a profession out of these things, and so then you have to go over swampland and swampland criteria, and you ought to go over Polchinski's book as well. So all these things later. And if you want to do string theory, it's a must that you go over these things at some point in time. Okay. And it's just the beginning. It's a nice beginning, I hope. So as I said, I'm not Professor Bafa, but I'll try to do a good job so that you get the basics at least at the end of this class. Okay. Yeah, I mean, what can I tell you? String theory is a highly mathematical undertaking. I mean, that's what I'm saying. This is at the level of college math, most of it. There's going to be in chapter 15 and chapter 16 some higher math, and also in chapter 22. But beyond that, it's just normal math, But string theory actually is a highly mathematical theory. Like Professor Witten got the Fields Medal for mathematics, developing mathematics in relation to string theory. So it's highly mathematical. In order to do it really, really well, you ought to have, and it's my opinion, of course, you ought to have a PhD in math as well to do professionally very well in string theory. Otherwise, you stay at a certain level if you don't know math very well. And you can have contributions. I'm not saying you can't, only with a PhD in theoretical physics. But to be top notch, you need a PhD in math as well. That is like that complicated. The actual, I mean, this is, I don't want to say that what we're going to do is a toy story. In a sense, is a toy story, in a sense, of string theory. But it's you have to start somewhere, if you want to professionally go into doing these things. In my opinion, you have to get, even if you don't get a PhD in math as well, at least you get to close to that level on your own work in order to write professionally savvy papers in string theory. So that I mean, this is just a warning for those who actually want to go into string theory. It's that complicated. So we study it at a basic level. Things are way more complicated later. Okay, so just a warning. Okay, I didn't go over Randall-Sundrum model. Let me see. I have 10 minutes left. I think I have to go over supersymmetry. And I'll skip conclusions, which is repeating pretty much what I already said. So let me jump quickly to supersymmetry and a bit of supergravity. It's basically supersymmetry mostly. Okay. So I have 10 minutes. I have to go over this in 10 minutes. So supersymmetry is a symmetry which transforms fermions into bosons and vice versa. Supersymmetry is appealing from the mathematical point of view as an extension of Poincaré spacetime symmetry, and a surprisingly unique as one unique one as it happens. So the Poincaré group, for the ones who studied special relativity, it's an extension of the Lorentz group. Lorentz group is based, there's those special relativity transformations from one system of reference to another. And what can happen in Lorentz group? Well, you could rotate one system of reference with respect to the other, or you could boost one system of reference with respect to the other, which means you take a direction in space and you fastly propagate one of the systems forward. And those boosts and those rotations are covered by the Lorentz group. Now, Poincare group is Lorentz group plus translations. Supersymmetry is an extension of the Poincare group, on the supersymmetry group. So that's basically it. And there are various representations of the Lorentz group, scalar, spinor, or vector. And there are representations, as we will see, of supersymmetry as well. And the extension from the Poincare space-time to include internal symmetry is via spinors. You don't know what spinors are because you didn't study quantum mechanics. You go look it up on Wikipedia. I don't really have time to cover Dirac equation. I recommend that you study a Weyl equation, Dirac equation on Wikipedia. It's okay. You don't have to be an expert. You just have to minimally understand these concepts. In order to understand superstring theory, you need supersymmetry. You don't have to really understand superstring theory in this class either, but as I said, we'll go over a little bit over the heterotic superstring theory, and so you need to know what superstrings are, what supersymmetry means. Otherwise it's just some words you'll hear and some formulas which won't make too much sense to you if you don't understand a little bit supersymmetry. And in order to understand supersymmetry, you need to know about fermions and bosons and how the Poincare group extends to the supersymmetry group. Okay. So the Poincare algebra is made up of these objects P and M. And M and P are the 10 generators of the Poincare algebra in 4 dimensions. P, the mu index goes over 4 components. So it's 0, 1, 2, and 3. So there are 4 P's and there are 6 M's. Not going to go over how just 6 remain. It's from symmetry. There are only 6 independent M's. So 6 plus 4 makes 10 generators because P and M are the generators of Poincare algebra. M is sort of an angular momentum, and P is the energy momentum tensor. And representations of the Poincare algebra are the scalar representation, vector representation, spinorial, like Dirac. You need to know a little bit about Dirac matrices. You look it up on the Wikipedia. For next time, you take a look. You start preparing your exam, right? So it's not going to be very detailed, the exam, but still you have to understand these things. That's why for your level, if you don't have the background in these things, Wikipedia is going to do a fantastic job explaining Dirac matrix, Clifford algebra and gamma matrices and Dirac equation and so forth, and Klein-Gordon equation and these things, and Hamiltonians for quantum mechanics, and a bit of special relativity, which you need, and a little bit of general relativity on the metrics and things. All these things, that's what I recommend. I recommended Carroll for general relativity. It's true. I didn't recommend a quantum mechanics book. It's true too. But the best thing is not necessarily to get the Carroll book, but to read a little bit on Wikipedia. I think that's your best shot. When you have some things you don't understand and you don't want to shoot me an email, you go to Wikipedia or AI. Learning with AI is okay. Answering the exam questions with AI is not okay. All right. So you can learn with AI, but the exam, you do it yourself. Okay. Okay. The Coleman Mandula. Coleman was a professor. I had the honor to be in his class at Harvard in quantum field theory. So he passed away. He was a very distinguished professor, Professor Sidney Coleman, and with great contributions to theoretical physics. And one of them is this idea that if you want, that's the theorem in a nutshell, the Coleman-Mandula theorem, says actually that if you want to extend the Poincare algebra, you can't do it with scalar or vector operators. It has to be something new. You cannot extend it in that sense. So then they said, well, okay, so it has to be spinorial because you can't extend the Poincare algebra in the same way like the space-time. It has to have internal symmetries, which they don't mix. And internal symmetries are these things that are spinorial and are related, you will see, to particles. I mean, you cannot extend a Poincare algebra in space-time. You have to do it with internal symmetries, which is with particles, and with a spinorial representation like these Q charges. And you need a graded Lie algebra, not a regular Lie algebra, because you cannot extend it that way. That's what is the no-go theorem of Coleman-Mandula. So after they learned this lesson from Coleman, they came up, Hagel, Pushansky, and Sonius came up with this idea that they will introduce spinorial charges, which are Qs. And the Hagel-Pushansky-Sonius theorem is something complicated, but it basically introduces anti-commuting charges, operators like Q, these Qs. So graded algebra, non-commuting objects. Poincare is commuting, supersymmetry extension, non-commuting. So the supersymmetry algebra is formed of the Poincare algebra, an additional algebra involving Q and Q bar, R and C operators. Q are n left-handed Weyl spinners generators. So people who know Dirac equation, there exists also when that's with Dirac spinners are the solutions of the Dirac equation. There exists something called the Weyl equation, where we divide the spinners in left-handed or right-handed. So sort of parity, left-handed, right-handed. It's really like that. That's parity. And you have left-handed, right-handed. And as I said, these are already not space-time objects. They are spinners, and they are related to particles. So it's a mix, if you want, in supersymmetry between space-time and these internal symmetries related to particles. Our symmetry generators transform their rotations from right-handed Weyl spinners to left-handed Weyl spinners. And C is something called central charge. We'll learn about central charge in the Virasoro algebra, and bosonic string in the when you quantize the bosonic string. So anyway, so I'll skip these, and now I'll just show you the supersymmetric algebra, and I'll finish immediately. Are these relations between the Q's and Q bars, and M's from the Poincare, and relation between M and Q's, P and Q's, and these are anti-commuting brackets. These are commuting brackets. So this is with plus between. You have to go over these. You have to look up these Poisson brackets if you want. Lie algebra brackets, and the anti-commuting brackets, their definition on Wikipedia. So to understand what these brackets mean, you have to do some work for this class. It's not very easy. And the R symmetry and the Q's and the central charges, these are the C's. And this is the supersymmetry algebra, much more evolved than a Poincare algebra. And now just a few words about representations. The n equals 1 representation of, or n equals 2 of supersymmetry, and higher than n1, 2, it's 4 and 8. These are extended supersymmetries. It is a spectrum of particles. The chiral multiplet with spins 0 and 1/2, a vector multiplet with spins 1/2, 1, gravitino, which is the superpartner of the graviton, because in supersymmetry, I forgot to mention that very basic fact, that bosons have a mirror in fermions. If you have a fermion in supersymmetry, there exists a partner, which is a boson. If you have a boson in regular life, there exists a superpartner, which is a gravitino. So in life, you have graviton. There exists in supergravity and supersymmetry a gravitino, which has spin 3/2. And the graviton has spin 2. And the n equals 2, the hypermultiplet, the vector multiplet, the supergravity multiplet. We'll see some of these things in the heterotic superstring theory when we get there. I have to kind of finish here some additional remarks here, which we will leave for some other time. You read the additional remarks yourselves. And I hope everything is okay. I have to pause now so that I let then Adrian pick up and go further in 10 minutes with the discussion section. I invite you to come back after 10 minutes to follow that. Yeah, it's going to be very helpful if you follow the seminars, the discussion sections for your exam. Okay. See you. Thank you for coming. I'll see you later. Enjoy your break. Okay, I think we need to start the preparations for the discussion section. Adrian, dacă vrei să faci share screen, să deschizi camera dacă poți. Nu e obligatoriu, dar
Uh,
nu trebuie să-l ai deschis. Și să share screen aplicația ta pe care o să scrii.
mhm. Sadly, I won't be able to open my camera because I have some technical difficulties. So yeah.
It's okay. If they hear you, it's fine. Don't worry about it. It's okay. So you just turn you just share screen the application.
There's an issue. Only the host can share their screen. So
Then how are you going to do it? If
great
that's not
question.
reasonable that you cannot share. I don't know how to do it. I should make your host tools. Um okay, let me share whiteboards.
I will try on the whiteboard, I guess.
It says here allow participants to share screen. Okay.
Okay.
I allowed you to share screen. You should be able
Uh,
to share screen.
okay, great. Okay. Mm,
Okay.
okay, is it
Yeah, it's
visible?
visible. Yeah, we see it. I see it.
Okay, great.
Okay.
So,
So
hello
I can,
everybody. Oh,
yeah, okay, go ahead. I'll just
okay.
mute myself.
Okay. Hello, everybody. I'm very glad to see you all here. My name is Zahri Adrian, and I'm from the University of Bucharest Faculty of Physics. And together we will hold the seminar for the summer string course. Now we should talk a little about some organizatory stuff about the seminar. First of all, the notes will be shared after the class with an additional PDF with the exercises and solutions. So it's best to stay focused on the explanations on the solutions. So don't stress about writing it down every time I write something. Okay. Secondly, there will be some homework. I think the teacher said it also, but I will say it again. Secondly, there will be some homework. It is not mandatory, but it's an extra preparation for the next seminars that we will have. Today, you won't receive any homework, but expect in the future there will be some. If you want to show me the homework that you did, you are free to do so. If you want to check your reasoning, if you understand everything clearly, but you can also, of course, just ask me anything about the seminar if you have trouble with it or you have proposals to make so it's a better experience for everybody. Now, if you have any questions about the seminar or you have some, I don't know, you want to give some advices, what you would like for me to do for you to understand better. Okay, if there are no questions, then we will jump right into it with the today's seminar. Okay, so for today, we prepared something more introductory for the subject. We can't really go like knee deep in all the mathematics in the string theory, so we are starting with some intuition about how stuff work. First of all, we will do some special relativity problems. One about Lorentz transformations in different coordinate systems. It's more specifically the light cone coordinates that we will use extensively along the course. And also an exercise about covariant and contravariant vectors, and also how we see if operator is covariant or contravariant, which is very important if we work with metrics, tensors, vectors, dual vectors, and so on. Okay. And finally, in the third problem, we will see some extra dimensions, how they work, how they appear in string theory more precisely. And it's very simply examples, so we built intuition. We will discuss especially about orbifolds, but it won't be like very difficult. It's more about visualizing it than anything. Okay, so starting off, we will discuss the first problem. If anyone of you don't understand how I write, or you need to ask me to write bigger or anything, please open the mic and let me know. Okay, so in the first problem, we consider the normal set of coordinates x0, x1, x2, x3. In special relativity, this is a position vector where x0 is defined as being the speed of light times the time coordinate. Okay, and x1, x2, x3 are just the special coordinates x, y, z. Okay, but we can also associate to this set of coordinates a different one to make a kind of a change of coordinates, which we denote, we will call them the Lagrangian coordinates that are denoted by x plus, x minus, x2, x3. Okay, where x plus minus is defined as being x0 plus or minus x1 over square root of 2. Okay, now we want to see how the Lorentz transformations change in this new set of coordinates that we will use, and perhaps see some intuition why it's better to use this set of coordinates. Okay, so for the first point, we will discuss a boost with velocity parameter beta in the x1 direction. So beta and in the direction x1. Now, if you remember from a special relativity class, or I don't know if everybody here had this class already, there are a set of transformation named the Lorentz transformation that move from the stationary reference point and the moving reference point. And these ones are like this. One moment. X prime 0 is equal to gamma x0 minus beta x1, and x1 prime is equal to gamma x1 minus beta x0, where gamma is defined as being 1 over square root of 1 minus beta squared. Okay, so it's just another constant. We don't, if you are not familiar with the special relativity, don't worry, it's just another constant. It's not something like a function or anything. Okay. Okay, so now we would like to see how these transformations change under the change of variables. To do this, it's easier to see how each coordinates x0, x1 change into x plus and minus. So because they are the only ones affected, because x2 and x3 are the same in both set of coordinates. So we write both relationships. X plus is x0 plus x1 over square root of 2, and x minus is equal to x0 minus x1 over square root of 2. Now, we might observe here that it is possible to get a relation for x0 and x1 if we simply add them together or subtract them. So by doing those two operations, we arrive at x0 is equal to x plus plus x minus over square root of 2, but also x1 is equal to x plus minus x minus over square root of 2. Okay, great. Now we have a direct way of replacing x0, x1 with the Lagrangian coordinates. And if we do this in the Lorentz transformations we did here, we arrive at x0 prime will be x plus prime plus x minus prime over square root of 2, which is equal to gamma times x plus x minus over square root of 2 minus beta x plus minus x minus square root of 2. Okay, and also doing the same for x1 prime. It will be x plus prime minus x minus prime over square root of 2 is equal to gamma x plus minus x minus over square root of 2 minus beta x plus x minus over square root of 2. Okay, great. Now we arrive at two relationships in terms of x plus and x minus. To separate them cleanly, we make kind of the same operation we did earlier to find the relations for x0 and x1. So here we just add them and subtract them again. So again, we do plus minus. And if we add them together, we arrive at 2x plus prime over square root of 2. Okay, which will be just square root of 2 to simplify directly, is equal to gamma. X minus with x minus it cancels out. We get x plus over 2x plus, which is again square root of 2. Okay, minus beta square root of 2x plus by the same logic we applied earlier. Okay, x square root of 2 simplifies, and we arrive at x plus prime is equal to gamma 1 minus beta x plus. So this is pretty interesting because initially we had the Lorentz transformation that depends on two coordinates, and now we have a scalar multiplication here. We just multiply it by a scalar, which is very useful, and it's much easier in the long term to use these transformations rather than the more complicated ones with more variables. Okay, and for x minus, we apply the same calculations by saying it's x minus prime, it is gamma times 1 plus beta x minus by the same logic applied here, but subtracting. Okay, great. Now this is the form for Lorentz transformations in Lycos. Okay, now we would like to see some other transformations to see how they work in different cases. So we'd like to see something different now, more specifically a rotation in the x1, x2 plane. Okay, one moment. Okay, so for point B, we want to see a rotation in x1, x2 plane. And here, if you guys remember the transformation, if you want to help me here. That's okay. We will get back to it further down the line. X prime 0 is the same as x0 because there is not really any relativity involved here. Is just a geometric rotation. So the time is not affected by just a rotation by an angle. Then we get x prime 1, which will be x1 cos of theta minus x2 sinus of theta. Okay, here it's not really clear. Okay, and finally x2 prime is equal to x1 sinus of theta plus x2 cosinus of theta. Okay, so this is the transformation that we have in the normal coordinates. Now we would like to see how they are changed in the light cone coordinates. So, okay, for this example, let's try to solve it together to give me some idea, some of your ideas, and to see how it goes. So, after we write the transformation that we will use, what should we do in the next step, considering the last point that we did?
We transform to light cone coordinates, right?
Yes, we write the individual transformation of x0 and x1 in terms of x plus and x minus, and just replace everything. And then we do some algebra to just get some nice result. Okay, great. So let's do that. We write first x prime of x prime 0 will be equal to x plus prime plus x minus prime over square root of 2. Okay, and it's equal to x plus x minus over square root of 2. Okay, after this we write x1 prime, which will be x plus x, no, sorry, x minus over prime over square root of 2 and is equal to x plus minus x minus over square root of 2 cos of theta minus x2 sinus of theta. Nothing changes there. Okay, I didn't miss anything. Good. Okay, and finally for x2 prime, it will be x plus minus x minus over square root of 2 sinus of theta plus x2 cosinus of theta. Okay, great. Now we have to somehow use these relations here to get equality for x plus prime, x minus prime, and x2 prime. Here it's a bit harder to see. I believe there's a lot of ways to do this, but I personally I believe it's intuitive to transform this part, not this part. Hold up. Wait. Okay. Let me just. Okay. This part to be something very similar to this, to be identical, and then we write the equality there. So to transform this to this, we have to subtract by x minus prime. We have to subtract by 2x minus prime over square root of 2 to be more exact, but whatever. Okay, so if we do that, we arrive at x plus prime minus x minus prime over square root of 2 which will be equal to x plus x minus 2x1 prime over square root of 2. Okay. Yes. Okay. Good. Now, this this one is just x1 prime, so it is equal to. Let me actually just copy this. Uh, uh, yeah. Okay, great. Good. Now we have only one x minus prime in one side, and in rest there's just x plus, x minus, and x2. So we can get here a nice relation for x minus prime. And if we do so, we first multiply by square root of 2. Equal to x minus x1, x minus times cos of theta minus square root of 2 x2 sinus of theta. Good. Now we move everything from the left side to the right side, the x plus and the x minus, and one moment. Okay, minus 2x minus prime is equal to x plus times cos of theta minus 1 minus cos of theta plus 1 x minus square root of 2 x2 sine of theta. So we get the relation that x minus prime is just cos of theta minus 1 over, no, 1 minus cosinus of theta over 2 times x plus 1 plus cos of theta over 2 x minus plus x2 over square root of 2 sine of theta. Okay, this is the relation for x minus prime. To arrive at x plus prime and x2 prime, we use the same algorithm that we used here. We just arrive at the same form for the order relation, and then we just simplify everything so it's just a clean relation like here. I'll leave it as an exercise for when you have time, because we don't have a lot of time. It's already uh, 7:25, so we should keep going with more interesting exercises, because this is more about calculations. I will also leave you the point C, which is about the boost in x3 direction, which is very similar with the exercise here, but it's instead of the rotation, it's the boost, and will be some some very similar calculations. So I will not go into much detail for this. Okay, so let's move to something a bit more interesting. I said about the four vectors for contravariant and covariant form, but for people who are not familiar with this concept, let's first say what is a contravariant vector. A contravariant vector is basically the the common thing, the common object that we use. It's just the vector that we use in high school. So we can define a mu as being, in our cases, because we use four vectors, it's a0, a1, a2, a3. But we also define an object named the covariant vector, for which we write with the indices down. The indices represent the component of the vector, so it's if it's a0, it's oh, one moment, this is a bit it's a bit important here to have the right indices. Okay. Oh, no. Anyway, okay, great. And for a vector with the indices down, it means we have a covariant form with the indices here down. The method of lowering the indices in differential geometry, which we multiply the contravariant vector with a metric. As the teacher said before, we don't really define very well in this right now the metric and what it does, but I'll talk very briefly about it. So we have the Minkowski metric in special relativity. We use this notation here with the value -1, 1, 1, 1, with zeros all in every other place in the matrix. Okay, so this is the metric for a flat space-time that we use in special relativity. In general relativity, the metrics are not as easy. They are very complicated to compute, but uh, we are not dealing with it right now, so we don't have to worry about it a lot. Okay, so let's just consider the metric, just this nice 4x4 matrix here. To lower the indices, we write a mu is equal to the Minkowski metric times the vector with the contravariant form, which means if we just multiply the two parts, the only component that changes is a0. So it's a minus a0, a1, a2, a3. So it's not really a very different object. It's just the zero component is with a minus sign. That's the only difference overall for now, for our understanding today. Good. So we would like to see first, let's first denote here the big difference. And in the rest is just A1, let's AI. Okay, good. So first of all, for this exercise, we'd like to see how the Lorentz transformations work on on covariant vectors. So point A, let's remember the Lorentz transformations from earlier, that A0 prime is equal to gamma A0 minus beta A1, and A1 prime is equal to gamma A1 minus beta A0. Okay, great. We've written again the Lorentz transformations. Now, how do we change this to be for the for the covariant form? What should we do?
We'll just replace the time coordinate basically.
Yeah, we
with
just add a minus sign to the A0 and the rest are just the same. Exactly. It's just like the example with coordinates, but now it's a bit simpler actually. So if we make the change, we get minus A0 prime is equal to gamma minus A0 minus beta A1 and A1 prime is equal to gamma A1 plus beta A0. Okay, by simplifying the minus sign here, we also get A0 prime is equal to gamma A0 plus beta A1. Okay, good. Now that is actually the entire first point, but in the second part, we would we would like to try something more interesting. When we talk about operators in physics, we would like to see in general if they are contravariant or covariant because we work a lot with tensors, metrics, and whatever. So it's very important to get the position of the indices right. So there's no issues when coming to calculations. So for a very common operator such as the derivative, it's crucial to figure it out if it's covariant or contravariant. So this is what we will try here. We want to see if the derivative operator is a covariant vector or a contravariant vector. Okay, so to do this, let's first write down the inverse Lorentz transformation. We will see later why. It's best to have it written down since the beginning so we don't have to stress. Okay, x0 is equal to gamma x prime 0 plus beta x prime 1. Okay, x1 is equal to gamma x1 prime plus beta x0 prime. Okay, great. Okay, good. Now, after we written the inverse Lorentz transformations, let's try to see how uh, the derivative changes with the change of coordinates. Not the change of coordinate, with the Lorentz transformation. Okay, to do this, let's first use the first component, the derivative of time. So we write down the derivative of x0 prime is equal to, by the chain rule law of derivative, we know that x prime 0 is a function in terms of x0 and x1. So we also have to get this into the consideration. So we this is equal to the derivative of x0 in terms of x0 prime multiplied by the derivative in terms of x0 plus the derivative of x1 in terms of x0 prime times the derivative in terms of x1. Okay, now that's why I said earlier that the inverse Lorentz transformations will be useful to have them from the beginning, so we see clearly what we should derive, so we get these derivatives here. Okay, so is everything clear so far? Does it make sense what we are trying to do? Okay, great. I'm happy everything is clear. Okay, so if we compute the derivative of x0 in terms of x0 prime, we get gamma plus 0 because the rest is considered a constant. It's not in terms of x0 prime. Okay, and the derivative of x1 in terms of x0 prime will be gamma beta, and the rest is just 0 because again it's constant. Okay, and we get these two nice derivatives. If we replace them inside the relation here, we get gamma, the derivative in terms of x0 plus gamma beta, the derivative in terms of x1. We can factor gamma out and get the derivative in terms of x0 plus beta derivative in terms of x1. But if we check at the last point we made here, it's the exact same form as the one for a covariant 4 vector. So this tells us that the derivative operator acts as a covariant vector. So we can just say that the derivative in terms of x mu is denoted by this vector right here. So this is also gamma x, the derivative in terms of the x0 plus beta derivative of 1. Sorry. Okay. So we showed that the derivative operator is covariant, which is great, amazing. Now let's see how we could use this for or some others or other operators. Let's say for the quantum operators for energy and impulse in the quantum mechanics. Okay, so we know that the energy operator in quantum mechanics is I h bar, the derivative in terms of time, and the impulse operator is just minus I h bar over multiplied by the derivative in terms of xi, where xi is just the spatial coordinates put together. Okay, but we also have defined in the spatial relativity class that we have the momentum 4 vector, which is minus e p1 p2 p3. This is the covariant form. The contravariant form is just e in here. Okay, great. So if we apply the same for the operators, we get that P0 operator is equal to minus E operator and is equal to minus I h bar, the derivative in terms of x0. Now, there might be some confusion about how we got from t to x0. We may use a natural coordinate, natural units where we can take c as being 1. So we can just go from x0 to t directly without adding an extra c. Okay, so we know that the P0 component of the operator is minus I h bar derivative of x0, and putting it together we get the impulse operator being minus I h bar derivative in terms of x mu. But we showed earlier that the derivative of x mu is covariant, so we write down just minus I h bar derivative x mu. Yeah. So this is a very nice, clean way to write everything down for these quantum mechanics operators. Okay. Great. We handle these transformations. So now we finished the part about the special relativity, and we would like to follow up with the extra dimensions part that we will encounter in the future, and we encountered today also with the Calabi-Yau manifolds and all the extra dimensions that we have. One moment. Okay, so let's see some intuitive ways of building these extra dimensions and how do we use them? Because in string theory, we don't use those classic extra dimensions we might first think about, like the X, Y, Z direction, which are very big dimensions. They are infinite, they are very large, and they are not, uh, realistically speaking, able to be 10 extra dimensions that are very large, like this. So instead, we use some smaller dimensions that come from identifications. By that, I mean, let's say we are in the park. We want to take a walk and walk around, I don't know, 10 meters. But we observe that after 10 meters, we end up at the same tree, at the same bench, or whatever. We can walk again 10 meters and so on, and we are just walking in circles. So from a one-dimensional trajectory that we have a straight path, we arrive at a two-dimensional shape, a circle. Even though it's a 1D contour, it's still a two-dimensional shape by this identification. And we can, it's not an infinite size dimension like the other ones. So it's a pretty intuitive way of thinking about it. You can think about it like adding a translation symmetry in some way that if we if we move everything a certain A, everything is just the same. So it's kind of like a symmetry, let's say, for the ones that are more familiar with this stuff. Okay. A second method of doing this are orbifolds, and we will discuss them more in detail in the exercise I'll be showing. Where instead of translation symmetry, it would be kind of like angular symmetry, where we walk on a circle, but each degree we walk is identified. Like, let's think about a pizza, okay? So we have a lot of pizza slices that are separated by equal degrees. And if we apply the identification, uh, each pizza slice would be the same one. So we would end up with just one pizza slice instead of a whole pizza. Okay, now that I explained a bit how it would work, let's look in some more visible examples. So, exercise 3, we would like first to see, one moment. Okay, so we want to construct a circle by making the identification x is the same as x plus 2 for a segment where x is between -1 and 1. So we draw here uh, the line. It's from -1 and 1. And we say that x is the same as x plus 2. So -1 goes to 1, and 1 goes nowhere because 3 is not on the line here. So after connecting these two, it's kind of like a rope that we connect at the end. So we get a circle where -1 and 1 are the same. And here it's also will be also very useful to have the point 0 written down here. Okay, and this way we get a circle of length 2. This notation here means that it's a sphere in 1 dimensions. If we had a disk, let's say, we would have a B2 because it's a ball in 2 dimensions. In this case, it's a sphere in 1 dimensions. I hope I'm remembering it right. Okay. Um, okay, after doing this, the problem also says that we also want to write down the orbifold as 1 divided by Z2, where we impose the identification that x is the same as minus x. In this case, is an identification with the 180 degree. So on this axis, these two parts are the same. So by just folding the circle in two, basically, we arrive at a, a line segment from -1 and 0, or 1 here. It is one moment. We are two fixed points that are uh, they are just the endpoints that are still the same here in the final form. Okay, so we go from a line segment from -1 to 1. We make it a circle. Then by using the orbifold identification, we get back to a segment which is half of its size. Okay. Now this is a pretty easy example. It's just a line that is divided by 2. So let's see something a little bit more interesting. Let's say we add an extra dimension. So we say that x is the same as x plus 2 and y is the same as y plus 2. Again, minus x and y is between -1 and 1. Okay, and let's see what happens in this case here. We also will do the same orbifold transformation. Okay, so let's see how it changes from the initial problem. Okay, this time we won't write the line segment. We will have a xy plane, which will be a square of length of side length 2. Y x. Okay, here is -1, 1, -1, 1. Okay, great. Now in this plane there are all the xy points that we will be interested in. Okay, so doing this we will arrive at a very famous shape in topology. For those that know about it, it's the torus, the donut shape. And I will show immediately how we get there. I mean, before using the orbifolds and changing it back somehow. Okay, so first we do the identification that x is the same as x plus 2. So this side of the square is the same as this one. So we denote them as being glued together by this arrow right here. And we do the same for y. So this and this is also glued. So, okay, this is nice. Usually people stop here when we are dealing with this type of gluing, but we will also see the visualization of it so we get a better idea. Okay, so making first the gluing between these two sides here, we arrive at a cylinder with um, open ends. Okay, Okay, after arriving at this, we glue also the ends of the of the cylinder. And after that, we get a shape that looks kind of like this. It's not very pretty now. I'm trying my best. I hope it makes sense. So it's a cylinder with the ends connected, so they're in a kind of donut shape. Okay, so from here we have this nice, interesting form. What should we do after this? We should also do the orbifolds because that's the problem. So again, we do the identification between x and minus x. So imagining a piece of origami paper, we have this side right here that is folded over this one. So such that the glued parts stay together. So let me actually get a new page here. Okay. After making the fold, we get a shape that looks like this. 1 minus 1 x y. So there is no identification left. I mean, instead, just these two sides right here, because the two sides that were glued before now they're overlapped, so there is no issue there. Okay, so now we also need to make the fold from this side to this side. So doing this, we arrive at a nice square of side length of 1. Okay, with with a very interesting geometry. It is called in topology a pillowcase, because these 4 points in the corners are uh, a bit more special. There are singularities because there is where the, let's say, paper was folded, so it's kind of a corner of the folded paper. And if we do some transformations, we can say that this shape is the same as of a pillowcase. So this was the more interesting topology part of this seminary, which will help us see more about uh, the geometry of dimensions later on when we need them. Okay, so this was all for today's seminary. Are there any questions? Are any curiosities? I don't know, anything? Okay, if not, I'm very happy I got the chance to have the seminary with you, and I hope I see you all the next time. Uh, yeah, um, I'm happy for you for taking this class, and see you in the future.
Oh, thank you, Adrian. It was a very nice presentation. Thank you very much for illuminating comments and explaining things so nicely to everybody. So that concludes our lesson for today. Thank you for coming. And there will be an email with there is going to, yes, Sarah, there's going to be a PDF file, not necessarily because you have access to the recording to review what he wrote, what Adrian wrote on the board. There will be a PDF file that will summarize basically what he said in a briefer solutions, not with so many details, but there will be a PDF file sent together with a recording, and you have access to the recording. You download the recordings, and you can review what he said during the discussion section. I hope you had a good time today, and I hope to see everybody next week at the same time, 5 p.m. Bucharest time. I wish you all a very pleasant week ahead, and see you next time. Bye-bye.
Thank you very much.
Let me stop the recording. I forgot that.